There we have it. And so I'll give a brief intro to Wouter. So Wouter is a PhD candidate at the Department of at the Physics Department at KU Leuven and the Geology Department at Ghent University. He's motivated by groundwater problems and using geophysics to image the subsurface. And he specializes in EM induction surveys, forward modeling, inversion, and uncertainty quantification. So Wouter, I will let you take it away.
Okay, thank you. So let's first check if you can all see my screen.
Yes, looks good.
Okay, perfect. So thank you for having me at this SimPEG seminar. So I'm Wouter Deleersnyder, part of KU Leuven and Ghent University, located in Belgium. And my talk today is going to be about flexible wavelet-based inversion within the SimPEG framework. But first, let me provide some context. The context of my PhD project is about methodologically improving Flanders salinization map. And first of all, Flanders is located in that yellow region in Belgium, which is the tiny country in Europe. And the salinization map is shown here, and it shows the depth of the fresh-saltwater interface. Like in this small map, only part of the salinization map is shown, but it shows the variability that is present, and also the interface is typically located at the depth of 5 meters. But first, I think I will have to minimize some other screen, otherwise I cannot point to it. Okay, so and a problem with this salinization map is actually that the inversion result is overly smoothed. It was produced with spatially constrained inversion. And an overly smooth inversion result has a large impact on the estimation of the depth of that fresh saltwater interface. And I will try to illustrate it with this image. So the blue line is an example of an overly smooth transition from fresh to salt. And first of all, we know that we have the typical overestimation of the low electrical conductivities and the underestimation of the higher electrical conductivities. And also the definition on which we define that the interface between fresh and salt water is located has a large impact on the estimation of the depth. For example, when you take this definition, we get this estimation. And while we have a slightly larger other definition, we get a quite different depth at which the interface occurs. While we actually know from expert knowledge that the transition between fresh and salt is actually more sharp, more like the black curve, where also actually the problem with the definition doesn't have a large impact on the estimation of the depth. So that's a little bit the context of the problem that I will try to solve in the talk today. So that map was created with time domain airborne EM data. So a helicopter flew over the polders, emitted a transient magnetic field. This induces eddy currents in the subsurface, which are proportional with the electrical conductivity of the subsurface. And those eddy currents produce a secondary magnetic field, which is typically measured somewhere in a receiver coil, also below the helicopter. To be more specific, the SkyTem dual moment system was used to produce that kind of data. And then the map was constructed with spatially constrained inversion. The step to go from that data to an actual image of the subsurface is typically done via geophysical inversion. But as the forward problem in this case is nonlinear, we usually use optimization to minimize this objective function. And the first term, that's typically the data misfit, and also typically the least squares misfit. And it tells you to what extent an image is in agreement with the data. But geophysical inversion in general is an ill-posed problem. So we can mostly think of an infinite set of inversion models that are in agreement with the data. And we solve this by adding this model misfit, which will try to filter out all the unrealistic images. And that's typically done in Occam's razor sense, meaning that if you have two inversion models that fit the data equally well, we should choose the image that is simplest. And that's typically done by adding a smoothness constraint. And then we get a spatially constrained inversion or Tikhonov regularization. But and this is also where we think we can solve this issue for our problem with the sharpness of the current salinization map. So the goal was to develop a novel model misfit term, which was a little bit more flexible. So we want to add a tuning parameter, which will allow us to get blocky, smooth, or in-between inversion models. And the idea is to use wavelet theory. So we will try to decompose the inversion model into the wavelet domain, which can be seen as viewing the inversion model as a series of building blocks. And then we combine this with the sparsity constraint, which is then combining this with, okay, a simple model is then a model that is built with the least number of building blocks. And while this principle has already been applied to geophysical inversion, we added a novelty, and that's the novelty of scale dependency, which is basically saying, okay, if you want to use smaller blocks, that's fine, but you have to pay a larger price. So they weigh more heavily in the objective function. So let us delve a little bit more into the discrete wavelet transform and why it works in this context. So here I show you a very simple model with only 4 model parameters for simplicity. And then I choose a building block. In this case, it's the Haar wavelet or the DBC1, which really looks like a building block. And then we will start the wavelet transform. And then this is basically this. This means that we have the first building block, the mother wavelet, which is basically the same as the one I showed you there. And then I make all these variations based on this mother wavelet, and they have different sizes, and also sometimes have different locations. And from here, you can actually already see that this building block, you don't need this building block to build that part of the model because that's flat. So that coefficient corresponding with that building block will be 0. And that's like the sparsity that is inherent in the wavelet transform for many inversion models. I'll come back to that later, but maybe introduce some notation. So these is what we call the wavelet coefficients. And as we had 4 model parameters to describe this model, we'll also have 4 wavelet coefficients, which we will also store in a vector. Then this is the mother wavelet basis function. And then these are all the wavelet basis functions, which have different dilatations, or there's wider and smaller building blocks, and at different locations, so at different translations. So let's look at another example where we have not a real realistic geophysical model, but a linear, I will also call it a model. Then I will choose a building block. In this case, it's DBC2. It's a little bit more regularly shaped, but I will apply that same wavelet transform to that linear model. And then I get this. So what I show here, I forgot to put on the titles, apparently. What I have here is that I have the wavelet coefficients. And what's actually quite remarkable is that we only need 3 coefficients which are non-zero to represent this signal completely, because all the other wavelet coefficients turn out to be 0. This is really the sparsifying nature behind the wavelet transform. But also, the first time when I saw this, I thought it was quite remarkable that irregularly shaped form building block can actually represent such a linear trend and with the perfect reconstruction. So maybe I can try to convince you with the following image. I'm not sure, but I will try to. So what I did here is I plotted those 3 building blocks next to each other. So I have one here from -2 to 1, and then another one step forward, and another one also 1 step forward. And then I multiplied it with the corresponding wavelet coefficient. And indeed, the first one was negative. Indeed, this shape is actually flipped. And when we sum them all together, you actually see the linear trend occurring between 0 and 1. What was also the case here between 0 and 1. So that's a little bit of the basics of the wavelet transform. But it's important to note that simple models have a sparse representation usually, while random models, like you just generate some random model, then also you will have like some random nature in the wavelet transform. So that's important because if the wavelet transform would be able to represent each model in the sparse representation, that wouldn't really work because we need the sparsity constraint in combination with the sparsity of simple or at least realistic inversion models. Some more definitions. I mentioned the DBC2. The 2 is actually standing for vanishing moments, which is here the P. And this tells you, in this case, that in fact the linear trend could actually have the wavelet coefficients, these ones being 0. That's actually part of this expression. And then DBC3, for example, could also exactly represent quadratic expressions and so on. And then another important aspect for the sparsity of a specific inversion model is also the compact support, but I will come back to this later. Compact support is the width of the building block itself. So in this talk, I will mainly use DBC wavelets, and these are defined in a specific way. And actually the shape, the resulting shape, which are shown for 6 different wavelet basis functions, are the result of imposing those properties. And the idea is that it is the wavelet with the minimal compact support for a given number of vanishing moments. And that's actually a very good property so that it can really represent many inversion models in a sparse fashion. Because when you have other wavelets which have larger compact support, it will turn out that it's generally has a less sparse representation. So it's less ideal to combine it with a sparsity measure. Okay, let's go to something more fun, I would say. So let's apply it, the scale-dependent wavelet-based inversion, to an example that you may recognize. So I plot the true models here for each, it's the same on each example. But then I apply our scale-dependent wavelet-based inversion with all those different building blocks. And for the first one, I've used the blocky building block, and then eventually our recovered model will also exhibit that blocky nature. While in the other extreme, when we use DBC6, which is rather smooth, we also end up with a rather smooth recovered model. And also, what's also quite interesting is that all the building blocks in between have features that are not that smooth and not that blocky, so they are rather intermediate. So that's already, I think, an advantage of the wavelet-based approach. And yeah, I think you may have recognized that example. It's actually taken from the SimPEG documentation. In the tutorials, there is a part on linear inversion, where those 2 examples are shown. The first one, for example, is sparse inversion with iteratively reweighted least squares, which generates blocky results. And indeed, you could compare this recovered sparse model with the blocky result from the wavelet-based inversion. While the more traditional linear least squares inversion results into smooth inversion results, which you then can compare with the recovered model with the DBC6. But what I also like about the wavelet-based method is that you have everything by only tuning one parameter. Because as a geophysicist or geoscientist, you want to tackle some geophysical inversion problem. I think you always start with trying out Tikhonov regularization because it's quite easy. You get smooth results, it's quite stable. And then, for example, in this case, you realize that Tikhonov regularization is maybe not the best decision. And you think, okay, maybe I should go for some blocky inversion, and you use the other method. Then I think it takes quite some effort to go from that type of inversion to the other one. You have to change from an L2 norm to an L1 norm. You will probably want to change your optimization algorithm. That will throw out some different errors than you're used to. So yeah, you have, again, still have to learn a little bit how the thing behaves to get acquainted with the new problem. So I think it's also an advantage of this method that it's, you have to learn at once with a specific optimization problem. And then you can have all those things just by changing one parameter. So I think that makes the geoscientific problem, which tend to become more and more complex over time, then I think this can make it a little bit more easy. So you can also use it by yourself, actually. So you have the clear SimPEG framework, and it makes sense that what I did with the wavelet-based regularization fits into this regularization part. And you can actually go and just pip install WABI, standing for wavelet-based inversion. And then what you can do is you can take an example from the SimPEG website. You have your normal import statements. You add the line where you import the wavelet regularization. And then where you normally define, let's say, simple or sparse regularization, you can put wavelet regularization. It also requires the mesh. And then you supply that wavelet basis function. In this case, it's just DBC6. And you can actually use the examples that are there and compare the results. And when you want to have a little bit more of information, on my GitHub, there is a little bit more information on how you can use it and the ideas behind it. Also, you may wonder what wavelet basis function you want to use. I have already mentioned the DBC wavelets. They are always the wavelets that I prefer to use, but maybe for your context, you're looking for some kind of other kind of behavior. So I recommend you go to this site where you can click here on all the wavelet families and see how they look like. And you remember that the shape of the wavelet family itself has a large effect on the recovered model. So maybe there is something useful there that you can use, and maybe you will use other wavelets than the DBC wavelets that I use. Maybe to end the 1D wavelet-based regularization, let me also maybe try to explain what's the added value of the scale dependency over the normal wavelet-based regularization. And that's clear with this example, I think. There is a black line almost hidden behind the green line, which is a true model. And then the blue line is showing the normal wavelet-based regularization without the scale dependency. And the green line fits the true model actually better. So that's the scale-dependent wavelet-based regularization. And the intuitive reason behind it is that I made it more expensive to use these smaller building blocks, which has led to the overestimation and a too narrow peak, and also this anomaly at the end of the inversion model. So that's the intuitive reason, but also for more like theoretical background, maybe you can check our publication from last year. And the main conclusion there is that for wavelets like DBC6, both methods tend to work equally well. But for the methods with the few vanishing moments, for example, DBC1, 2, or 3, it's really as an added value to have that scale dependency. And this just allows us to use the whole range of the DBC range from 1 to 6 and higher to get like an ensemble of inversion models. So yeah, let's put this as the first conclusion. But let's go back to the salinization map itself. So we had the problem with the sharpness of the current salinization map. So let us first look at the synthetic example, which is realistic for the salinization map. So here is a synthetic example where a highly conductive saltwater lens is lying on a clay layer and with some freshwater on top. So I've used SimPEG to generate reliable multidimensional data on an accurate 3D mesh to get some reliable synthetic data. And then I used the wavelet-based method to invert that data in 2 dimensions. And the extension to 2 dimensions, I had to make some choices. And I decided to make the choice for maximum flexibility. And it's actually the same approach than, for example, the Tikhonov regularization implemented in SimPEG, where you have a separate misfit for the horizontal and for the lateral, the horizontal and the vertical orientation. And this allows us to use a different wavelet, let's say, a different type of structure along the vertical orientation and a different type of structure along the horizontal orientation. And especially with other wavelet-based methods, which tend to use the higher dimensional wavelet transform, the disadvantage there is that you have the same type of structure along each orientation. And I think that's not always suitable for geophysical inversion. So when we run the method, we can get like a whole ensemble of inversion models. Let's say, for example, the first one, we have used the blocky inversion along each orientation. So we definitely also expect and see some blocky results in the inversion model. The inversion model itself fits the data up to the noise level, but it's not really the inversion model that we expect in real life. So maybe other wavelets combinations are more suitable. For example, in this case, I have changed the lateral wavelet basis function to DBC2. And then we see definitely a sharp but smoother transition along that orientation, but we still recognize the distinct steps when you go along the vertical orientation from the DBC1 wavelet. And then this example is the opposite, where I have used a very smooth wavelet basis function along the vertical orientation, and then the blocky along the horizontal one. And in this whole set of inversion models, you may think that, for example, this combination is in a good agreement with the true model. But still, for this approach, you have still your regularization parameter, and then that regularization parameter, the relative one. In SimPEG, it's like alpha x and alpha y, but one of them is redundant, so I take them equal to 1. And then I say this is the relative regularization parameter. So in an ideal world, you would want to optimize for both regularization parameters, which isn't generally a problem, but with the flexibility of this wavelet-based method, and actually due to the specifics of the wavelet transform and also the scale dependency, it can happen that when you combine different wavelets, the value of this this term is not properly scaled with the value of the other term. And then you get some very weird inversion models, which you actually do not want. So I tried to solve this with a calibration step. And from a helicopter view, the idea is as follows. So you look at the variability that you can see in the data itself. So if you see a lot of variation here, you expect also to see more lateral variation in your inversion model. What you can also do is to take some random soundings and to do 1D inversion. Then you only have one regularization parameter, and then you can fit up to the noise level. And then you get some idea of the complexity to expect along the vertical orientation. The specifics of the calibration step itself are a little bit more involved, and the details are actually described in the preprint available on ResearchGate and Archive. But at least this calibration step leads to a more objective choice of a good candidate for alpha, which I call alpha tilde. And when I show this for a few wavelet combinations, for example, DBC1, this is almost 1, which is also a good result, showing that when you use the same wavelet combinations along each orientation, you get not a very distinct result. So the scaling is right. But here we see when you use DBC5 in combination of DBC1, the optimal estimation is quite different than DBC1. So that's something to take into account. Also, I would recommend that if you do this step, that you still go one step further and do some sweep along that alpha parameter to really let your expert knowledge to use your expert knowledge. And for example, in this case, what I did is I took the DBC1 and I varied the gamma, and the gamma multiplied with the estimated alpha leads to the real alpha present in this equation. And for example, in an extreme case here, you see some very stretched out blocks along the vertical orientation. And in the other extreme case, we see some very stretched out blocks in the horizontal orientation. And my decision was that actually this example with gamma equal to 5 is optimal, or is at least looks good compared to the synthetic model. And then maybe let me note that when you go back, I have used this gamma throughout all other inversion models. So I only had to do this calibration once on DBC1. So I only had to do this sweep once, and then I've used this gamma, which I determined there, to use for all inversion models. So the alpha tilde will be different for each inversion model, but the gamma will be the same. So you will be able to combine some kind of objective step with your expert knowledge, and then you finally end up with a suitable candidate for alpha. Okay, let's go to the actual field data itself. And there I took a slightly different approach. So the field data is the data behind salinization map, so the airborne EM dual moment stuff. And there we will try to incorporate our prior knowledge based on via that wavelet basis function. So for example, we expect some sharp transition from fresh to salt. So maybe we should choose some sharper wavelet basis function. So for the vertical orientation, I choose a rather sharp wavelet basis function. While for the horizontal orientation, it's maybe more expected to have some smooth transitions between the model parameters. So why not taking a smoother wavelet basis function? And then this is actually the result that we got, where these white bands are actually data that was missing, which can happen on field data. And then this is also like an approach to get some result. Timing wise, I think I will skip those slides and end with a nice end of the story with some future work left. Recently, I was awarded the Brilliant Marine Research ID grant, and I'm really happy with it because with that grant, I will be able to collect some high resolution ground-based data. So ERT, borehole loggings, and also ground-based time domain EM, which will enable me to have a really high resolution image of a subsurface. And then I will use this to calibrate it against the ensemble of inversion models that I got from the airborne EM data. And then I will be able to make a more informed decision on what wavelet basis function in combination with the appropriate parameterization that will be suitable. So yeah, I'm actually quite looking forward to get started on this project. So if you have any questions, I would be very happy to answer them.
Excellent. Thank you, Wouter. Yeah, feel free to unmute, jump on in if you've got a question. And if lots of people do, we can do raise hands, but feel free to just jump on in.
Hey, Wouter, thanks for your talk. It's really interesting. Could you please go to the page 10?
This one?
The maybe next one. Oh, yes. So if we look at the top right figure showing here, the maximum value for the blocky model is much larger than the smooth L2 norm recovery model as well as the true model, if we use the sparse norms. However, if you look at your models, the maximum value for the blocky model and the smooth model looks highly consistent. Could you please explain the reason behind these observations? Because this is my first time to see this.
Yeah, that's actually also something we have observed in the paper we published last year, is that is even with the DBC6, okay, you get smooth results, but they are able to get higher amplitudes. There are some nice examples in that paper. So when you have like a huge peak and you still use a smooth way of recovering that model, you are still able with the wavelet-based method to get that peak which is almost not possible with smoothness regularization. So that's like a property typically of a wavelet-based inversion.
Oh, okay, okay. Yeah, that's a really.
I'm not the only one who observed it, by the way. So it's confirmed by others as well.
Yeah, this is really interesting properties for the.
And that's actually
Variance.
when I can go a little bit further on this. Like in this example, there will be then, for example, a few of these coefficients which should not be zero, but then really explain that specific peak because they correspond with the right location on that place where you have the peak. Imagine you have this large peak here. There will be some very distinct building blocks that will be able to explain that data and still be able to have sparse representation. So that's why the wavelet theory is able to have that peak well recovered.
Okay.
But yeah, maybe with some other examples at some other time, I can elaborate on this.
Yeah, looks interesting. Another questions relate in the page 16. Yeah, so the first problem is how do you define the smoothness and the blocky? So I mean, what's the center level of the smoothness is a smooth model? For example, in these 8 models, so which one is a start from which model is smooth?
Well, when you use, for example, this one, you use smooth wavelet basis functions along each orientation, thus you get a smooth inversion result. I don't have the profiles now in the slides, but yeah, you also see a smoother transitions when you put the profiles on top of each other. But yeah, you can also combine them. For example, here, yeah, it would be nice if I have the figure that shows like this cross-section. This cross-section will be rather smooth, while this cross-section will be blocky. Okay. So yeah, both, I mean, if you use a wavelet basis function with a large number of vanishing moments, you will get smoothness along that orientation. So also this one will be rather smooth along that orientation.
Yeah, I'm thinking, is there any ways we can compute values and the quantity to evaluate the smoothness for this model? Yeah,
I haven't considered it. Yeah, could be, yeah, maybe interesting to quantify it.
Yeah, and another quick thing is I noticed that the RMS values looks the different for these 8 models.
Yeah,
and the most in the bottom right models is 1.7, and in the top middle one is 0.68.
Yeah, that's true. That's mainly because yeah, we need to generate all these inversion models, and it takes quite a while. So you have like 68 landings. You have some optimization to do. So the discretization for the absolute regularization parameter was not small enough, let's say, to really hit the root mean square error equal to 1 each time. So that's the reason why it's not always equal to 1.
Yeah, but so are they? So my point is, are they still fit the data in the same levels? If they cannot fit the data in the same levels, probably it's unfair to compare these models in.
Yeah, but yeah, in fact, that's a fair point. It should be more ideal if they all are equal to 1. But yeah, that would take yeah,
maybe
quite some extra effort to generate these inversion models.
Yeah, yeah, I understand. Yeah, maybe in the small range, like 0.8.
Yeah, you never know when it will hit. So that's because yeah, you don't know what the values of the model misfits will be. So it's always a little bit of a guess. And then suddenly it goes really quick, and then it overshoots or undershoots, and yeah, you have a too low value.
Yeah, we just need to have a smarter way to come back up, right? You're using a cooling schedule for beta. Is that the reason, Wouter? Yeah. We need to be able to just at the end, you know, have a little time to bring it back to target, basically. Yeah.
Okay. Yeah. That would be yeah, more suitable in this case, and also save some computation time, I suppose.
Well, and then at the end, because you'll need to reiterate to just readjust. But anyway, yeah, it's a linear, it's a linear system, right, Wouter? The whole thing is linear. Is that right?
I'm sorry?
Is the iteration process linear? Is it a linear system that you're solving with the wavelets?
Not sure what you mean actually.
Well, is it like your regularization term? Is it model dependent, or is it is just a linear linear operators that are inside? Is it?
Yeah, I guess there are linear operators inside. The model misfit is not the computation issue. That's really fast. If that answers your question.
Yeah, I'm guessing it's a linear system. Yeah, that's okay. Great talk, by the way. I need to jump. I need to quit to go to another meeting soon. So I'll just tell you two things. One, it sounds like you're really ready for a PR to bring your stuff to to SimPEG main. Looks like your regularization class is like perfectly in line with what we're doing. So it would be great if you have a pull request and bring your stuff, right? So then we can help you basically maintain it over time, and we can use it, more readily.
Okay.
And then the second thing that I wanted to ask you, so comment to the alpha values. So usually we use the alpha values to as a parameter for people to tweak, but at the same time there's a lot of like dimensionality that happens. Let's say you have a model regularization and you have a gradient term. We use the alphas to scale those dimensionally with each other so that they can play nice, right? Let's say the standard alphas is going to be 1/dx squared. That's kind of like the usual thing. Yeah. And here you're kind of combining different wavelet functions. So is there any dimensionality, big offsets between, let's say, dB1 and dB5? Because that's usually where alpha is coming in. Yeah, sorry.
Yeah, I think the problem is actually the scale dependency here, because depending on the length of the signal, so if you have more soundings, let's say you have a wider image and a wider mesh, but this will have an effect on the amount of wavelet levels. So the amount of times you take smaller building blocks, and when you take a smaller building block, the way that you will assign to it will be a power law, so 2 to the, let's say 4th and 6th and so on. And this is, I think, a little bit the reason why it doesn't scale like you would expect.
Right. But is there any, like, I'm just going to throw it out there, if there's any obvious constants that needs to be accounted for if you're going to combine, let's say, a dB1 with a dB5, right? Like, let's say one has peak amplitude of 1,000 and the other one has a peak amplitude of 1, then implicitly that your alphas needs to have at least 1,000 coefficient in front of them to combine them. Does that make sense?
Yeah, it makes sense, and it's something that I tried to solve with various methods that made sense, and then eventually didn't work at all.
So you did it empirically. Yeah.
This is like the best I could find.
I gotcha. Yeah, sounds good. Perfect. All right, I gotta go. Good talk. Congrats.
Okay, thank you.
Yeah. Good luck with finishing your PhD. Bye.
Maybe while we wait for others to come up with questions, one thing, when you were sort of pointing out where in SimPEG these changes take place, you pointed primarily to the regularization. But if I'm understanding correctly, would it also be a mapping that you need to apply, or is it?
Yeah, and in the current implementation, I don't need the mapping. I used to do it. I used to optimize in the wavelet space. But when you do this, when you go to multiple dimensions, this doesn't work when you take this approach. So it's basically, it's basically the chain rule that solves the problem, which is important, which is in the derivative of the model misfit. So it really fits really nicely, I would say, into SimPEG. Doesn't require an additional mapping.
Interesting. Yeah. So you would still presumably invert for like log conductivity, but then the regularization is where all the wavelet magic is happening. Oh, cool.
Yeah.
So I'm wondering, did you use the SimPEG optimization modules to solve this cost function, or you write?
Yeah, not for this, because when I was developing it, things get always too messy, and then you work with your own codes. And actually, for this one, I worked with the BFGS in SciPy, which I also, which is all, is great actually for this purpose. And also, I think a little bit faster than it's SimPEG for this case.
I see.
Wouter, may I also ask a question? Hello, everyone. Yeah, I know Wouter quite well because I'm one of his promoters. But I'm coming from a more, let's say, theoretical physics and mathematical viewpoint. Actually, here you have sliced up in vertical and horizontal direction. What prohibits using genuine 2D wavelets? Do you win or lose something by not doing that or doing it?
Why I don't consider 2D wavelet transform?
No, I know, but would that change anything? Could that help, or is it computationally harder?
The 2D?
Yes.
Well, first of all, then you're really limited to square images. And for example, when we go to this image, it's definitely not square. We have 300 soundings, and the discretization and the depth is only 64. And if you would need to extend it to like 300 also, and that orientation, when you use analytical models, for example, it's not really, it's not really computationally efficient. So I think it's better to have a method that is suitable to not do some computational overkill. Also some other people use shearlets, which then also take into account some directionality. But the amount of model parameters that you have, it's
explodes.
Yeah, and then you need to optimize for all of them. For not much gain for this application.
Okay, thanks.
Folks have any other questions? Yeah, go for it, Peter.
Yeah, and do you think it would be straightforward to extend it to 3D, or you see any difficulties?
Yeah, I don't expect any difficulties. Well, I also didn't expect that difficulties to go to 2D, but then the calibration was like a hard thing. But now I expect that I can do the same thing into 3D, which I will actually also try for this step. I will try to do to get some 3D geological model to use this to compare with the high resolution data.
Cool. Yeah.
And here, just to clarify, when you said 2D, was it 1D forward simulations and then 2D regularization?
I think I once used 2.5D, meaning that you have only variations in depth and one direction, and then all constant along one direction. But the imaging itself use a 1D for model, and then I call it quasi 2D.
Okay. Excellent. Okay. Any last questions? A minute or so.
Nope.
If not, thanks so much, Wouter. It's really exciting to see your work and so cool to see. I think, one of the things we strive for and the ideas we had with SimPEG is that it be modular so people can plug in new pieces. But it's really nice to actually see that's possible, and you've done some really cool work. And so, yeah, to Dom's point, if it's something you're interested in including in the main SimPEG, I think we should absolutely follow up on that and chat through that.
Okay.
And best of luck with the next stages. Congrats on your award. I'm really excited to see where you go and where you continue to go with this.
Okay, thank you.
All right. Thanks so much. I'll stop the recording here.